till now, what we've been talking about is how to solve, or what does the analysis problem mean. And we said that if you want to if you want to find out the displacement field everywhere in your structure, then the equation that you need to solve is the equation of equilibrium in the deformed configuration, right? So we tried to find out what that equation of equilibrium would be, and we found that this divergence of Cauchy stress plus the body force equal to 0, that should hold at each and every point in your structure, right? So this is the equation of equilibrium that we want to make sure that holds. And in addition to this equation, since we want to find out the displacement field, we actually need a couple more relationships. So one thing we need to know is how is the strain related to the displacement, and how is the stress related to the strain. So those two types of relationships are the first, the strain displacement relationship, and the material model, right? And then today we're just going to try to find out more about how bodies deform. What is the kinematics of the deformation? Till now what we've been doing is called kinetics. So kinetics is when we try to work with forces, we are trying to figure out why deformation happens. That's kinetics. And today we are going to talk about kinematics, which is description of the motion. How does deformation occur? We already know why it occurs. We applied some load, it is going to deform. But now we are going to try to describe how it deforms. So that's kinematics. So last time also we introduced this thing called the deformation map. All that it says is that if you know the position of the of some point in the original configuration, where does it go? So that relationship captures the deformation map. And we talked about how strains are related to the changes in deformation. So the first measure of the changes in deformation is this very important measure called the deformation gradient, F. And as I mentioned here, F is a tensor. The way that this tensor is denoted is with this sort of a notation, that a derivative of x in the final configuration with respect to derivative of x in the initial configuration. Now you might be wondering that how do you take a derivative of a vector with respect to another vector, but don't worry about that. This is just a notation. And if you are still want to know more how to do that, all that this does is it creates a matrix where if the final configuration is given by small x, small y, small z, and the initial configuration is big X, big Y, big Z, then deformation gradient F can be represented with this matrix. And again, I'm calling this as a representation of the deformation gradient. This is not a tensor, this is a matrix that represents that tensor. Another relationship, if you just go back to here, to this, x is equal to the original location plus the displacement. If you take the derivative of this with respect to big X, what you will get is that deformation gradient is nothing but identity plus the gradient of u. So this is another relationship that holds between the deformation gradient and the displacement. So now this might be a lot of mathematical expression, but the way, or one good way to interpret the meaning, the physical meaning of F is that it takes vectors, small infinitesimal vectors from the undeformed configuration, big delta x, to the deformed configuration. So these are small infinitesimal vectors from the undeformed configuration. If you deform it, F takes it to a deformed configuration. And if you express that relationship in terms of matrices, that relationship holds like this. So let's say I was telling you last time that you have this body. Go to any point in the body, okay? And now you're going to try to imagine a small, very small infinitesimal sphere around that body. We're not talking about equilibrium anymore. We are trying to find out how our infinitesimal vector is going to deform. Okay? So that's why we take this small infinitesimal sphere around this point. And we can show that the only effect that f has on this on this sphere is that it can turn it into an ellipsoid. There's no other possibility for f to do. But last time I might have mentioned, that that in all of continuum mechanics, this is only the mode, which is not quite true, because f is only the first derivative of this x. Nobody is stopping you from taking higher derivatives. And if you take higher derivatives, then you can model something more complicated than an ellipsoid. So those are called gradient theories, but we'll not get into that. So for us, we will stick to that f, the deformation gradient, is going to take small infinitesimal vectors from the undeformed configuration to the deformed configuration. Okay, and that's all that a tensor does. It takes vectors from one space, and it produces vectors in another space. That's what our definition of tensor was, right? So keep in mind this relationship, that f is just going to take small or these vectors into these. And last time I think also there is a error here. So how many of you have heard of this spectral decomposition of a matrix? Anybody heard of the spectral decomposition? Okay, some of you have heard. So what this spectral decomposition means is that once you have a matrix, you can express that matrix in terms of its eigenvalues and eigenvectors. Now, this matrix F in general is a non-symmetric matrix. So in general, non-symmetric matrices will not have real eigenvalues. They can have complex eigenvalues. So this fact here is not correct. These are not the eigenvalues of F. They are eigenvalues of another tensor called U, and I'll tell you in a little bit about that. So what we are trying to say here is in this relationship right here, if you go to some vector big N, so I've marked those vectors in this undeformed configuration as these big N unit vectors. When you apply F to these unit vectors, it will take them to a new direction, N1, and all that it will do is that it will stretch it by some scalar lambda. Okay, so what that means is if you try to imagine one small unit vector along this N1, big N1, when it deforms through F, it is going to go to small N1. Okay, and it's not only is it going to go to small N1, but its length is going to change by an amount of lambda. So what that means is that this sphere will go to an ellipsoid, which will have semi-major axes along N1, N2, and N3, which are going to be of the lengths lambda 1, lambda 2, lambda 3. So all that we are doing is we're taking a sphere and stretching it and perhaps rotating it. Okay, so that's the effect of F on any infinitesimal vector. Does that sound clear, or okay? So keep this in mind, and now let's try to figure out how can we define strain. Okay, so now this is a handout I was supposed to bring today. I don't know, I've left it somewhere, but but take along notes, and I'll post this PDF online anyway. So yeah, we were talking about how this F takes vectors from the undeformed to the deformed configuration. Another way of decomposing this F is called the polar decomposition method. What it says is that we can imagine the effect of F as a combination of a pure rotation R and a symmetric tensor that only stretches the principal directions. So this F is equal to R rotation tensor times U a symmetric stretch tensor, which is equal to a different stretch tensor times the same rotation tensor R. Okay. Now, did you guys do this last semester in 570 polar decomposition theorem? No. Yeah. This thing will help you to try to understand what is the physical meaning of this F, how does it deform, and all that. So another way to interpret this is like this polar decomposition theorem is like this. We know this relationship right here. Small delta x is F applied on big delta x. That is, big delta x vectors. You take any big delta x vector, it goes to a small delta x vector. This can be written as R times U times delta x. Now, if you consider this as the relationship, and another way to interpret this relationship is that this tensor U is going to act upon these small delta x vectors, which is here. So these are small delta x vectors, and the tensor U is going to act upon them to basically stretch it along along some directions. Then you can take those resulting vectors, all these resulting vectors, and apply a rigid body rotation, a pure rotation, and that will lead you to your final configuration. So this is one way of interpreting the effect of F, that it is a stretch followed by a rotation. But keep in mind that it is written as R times U. So it just because we have R on the left and U on the right, it doesn't mean that R goes first. We are multiplying delta x with U first, right? That's why U is applied first and then R is applied. So similarly, now this is called the right deformation mode, and there is another way to imagine this is the left deformation. So if you say that F is equal to V times R, then again if we combine these two, then what we are saying essentially is that we are going to take these small delta x vectors, all these small delta x vectors, and apply a rigid body rotation to that. So if we take a sphere and we apply a rigid body rotation to it, it stays a sphere, right? The only thing that happens is that these vectors n, they get transformed to the final small n vectors. And now you can apply a pure stretch to it that will lead you to, again, the same kind of a final configuration. So this is a way to interpret the effect of F. Okay, and why is it important? Right here. So we all know that strain in a body is measured by the changes in the deformation. But how do we classify a case when strain would be 0, right? So what we are saying is that if the initial configuration is something like this, all the initial vectors are like this, and if we apply a deformation F, and it still stays the exact same sphere, but perhaps there are some directions that are rotated. It's a rigid body rotation. So if you take some finite sized body and you just apply a rigid body rotation, there should not be any straining, right? So if there is if we can say that that thing holds for each and every point, that you go to each and every point, and the only effect of this F is to rotate it in a rigid body way, then we can say that the strains are 0. Okay, and how do we find out this condition? What does this condition mean? So now note that the equation of a sphere in the undeformed configuration would be if you take any delta x vector, take one delta x vector, dot it with itself, right? So all that we are trying to say is that pick a point on the sphere, take that vector, dot it with itself, that should be equal to radius square. So I'm saying that this epsilon is some small number, some micrometer, nanometer, whatever. This is epsilon is some small number, and this equation denotes the equation of this sphere. In the final configuration, I know that all these small vectors are my small delta x vectors. So all these small delta x vectors, the exact same equation must hold. That small delta x dotted with itself should be equal to radius square. Okay, so that's the same equation of the sphere. Now since this epsilon square or radius square is this equal to radius square, therefore this quantity should be equal to this quantity. And if you write that out, this is delta x on the left side. This is small delta x dotted with small delta x on the right hand side. All I've done is that substituted the equation that this small delta x is actually f applied to big delta x. And I can rearrange these terms in the following way. Okay. All I've done is, since I can say that two vectors, when they are dotted, I can also, let's say you have two vectors a and b. If I'm trying to find out a dot b, then I can also express that as a transpose b in matrices, right? So if you do that, what you will get is this. And now since this has to be equal to this, the resulting equation that you get is that delta x dotted with f transpose f minus I times another big delta x should be 0. So this is the condition. This is the condition that must hold if the strains are to be 0. Okay. So now this part right here, is the condition that if this part right here is equal to 0, then we can say that the strains are 0. Okay. So based on this, what we'll do is we'll define a couple of deformation tensors. So we're going to say that this f transpose f, and I don't know why this is not coming out. Okay, that's better. So we're going to say that this term right here, f transpose f, that is equal to C. We are just defining a new quantity. This is also called the Cauchy-Green deformation tensor. Did you guys hear about this last? Okay, yeah. So so when you take this, you can also express it in terms of the polar decomposition. So take a look at this. That any f, whether the deformation gradient f has some rotation and stretch, it wouldn't matter to C. So f is equal to Ru. That's coming from the polar decomposition. Transpose again Ru, and since this thing can be expressed like this, and the R transpose R, since R is a pure rotation, R transpose R is actually equal to identity. Okay, this is an orthogonal matrix, so, or orthogonal tensor. So this becomes identity U transpose times U, since U is symmetric, becomes U square. Okay, so what we are saying is that this green deformation, Cauchy-Green deformation tensor is simply equal to the stretching square. Now note that earlier when we started, we said that f is equal to R times U. So if we wanted to use f as a measure of strain, we would get a finite strain even if the body had some rigid body rotation. But now this tensor C has eliminated the effect of R. So even if there is no rigid body, even if there is rigid body rotation, C will not take into account the rigid body rotation. So C will take into account only pure stretches, pure straining. Okay. So yeah, going back to this spectral decomposition, once you know that this deformation C, which is a part of that condition, we said that for no straining, this U can be expressed in the spectral decomposition like this, where lambda I is the eigenvalues of those stretches. So again, if you take a look at this, um, let's say Ni, this big Ni is one of the principal stretch directions. So what U is going to do is take this unit vector along N1 and it is going to stretch it by lambda 1. Similarly, it is going to take N2, stretch it by lambda 2, N3 and stretch it by lambda 3. So that's the only effect that this U has. And once you know the spectral decomposition of U, that you can express this as set of eigenvalues times the outer product of its eigenvectors. So remember that N is a matrix, a column vector, and this cross product is a row vector. So when you take vertical times horizontal, you get a matrix. So this is just a outer product of a matrix. And then you take that matrix, multiply it with lambda 1, add lambda 2 times another matrix, lambda 3 times another matrix, you get this stretch matrix back. So the same way the C can also be represented, the deformation tensor C can also be represented in terms of eigenvalues and eigenvectors. And the important thing to note here is that the eigenvalues of C are actually the square of the eigenvalues of U, which are the exact same lambdas that we had in terms of the spectral decomposition of F. Okay. So the way to see what are the physical significance of these deformations is, try to imagine this small infinitesimal cube. So again, let's say that this is a cube of side 1 micrometer or some very small number. In the limit, we will say that this goes to 0. So the effect of F and effect of U and C, all that it does is, if you have unit sides in the undeformed configuration, it is going to stretch and rotate it, and it is going to finally produce a cuboid. And all these angles are still going to be 90 degrees. Okay, you start with a cube and it produces a cuboid because we are considering this cube along these principal N1, N1, N2, N3 directions. So it produces a pure cuboid. So now to see the significance of what are all these components, what we use is invariants. Invariants of the tensor C. So anybody heard of, does anybody know what an invariant is? What is an invariant? Yeah. With right. So invariant is, what that means is, I was telling you last time that a tensor it can be represented with a matrix if you choose a certain coordinate system, right? So if I choose a certain coordinate system, I can represent my tensor as a matrix. Now if I choose a different coordinate system, the components of my tensor are going to change, right? But there are some quantities of a tensor that does not matter which components you choose, they will not change. That's why they are called invariants. They are invariant with respect to coordinate system. So some of the invariants that you see for a tensor are like this. So one of the simplest invariant is actually the sum of the diagonal terms. If you take C11, C22 plus C33, that's the sum of the diagonal terms. That's represented with this. And again, there is a summation over I, so you are going to interpret this as C11 plus C22 plus C33. And this is also called the trace of this tensor C. This can be represented simply as the sum of the squares of the eigenvalues. So the eigenvalues of C were lambda 1, lambda 2, lambda 3 squared. So if you sum up all the diagonal terms, this is what you are going to get. So physically, what does this mean? So I was talking about this unit cube, and when it deforms finally, it goes to a state uh, where the length along n1 is going to be lambda 1, the length along n2 is going to be lambda 2, and the length along n3 is going to be lambda 3. Okay, so can anybody uh, take a guess or try to figure out what does this quantity physically represent? We had a unit cube of side 1 to start with. It went to a cuboid with sides lambda 1, lambda 2, lambda 3. So what would this quantity represent physically? That's right. So if you try to consider a diagonal starting from the 0 point from the origin and draw a line here, what is the length of that line? Right? So starting from the origin to the diagonal right opposite corner, what is the length of that diagonal? You would say sum of the square of the components. So that's lambda 1 square plus lambda 2 square plus lambda 3 square. Right? And that's the principal invariant, the first invariant of C. So similarly, what do you think is the physical significance of this? The second invariant. What is lambda 1 times lambda 2? So this is lambda 1, this is lambda 2. What is lambda 1 times lambda 2? Is the surface area of this face of the cuboid. So once you take that surface area and square it, you get the first term. You take the surface area of this face of the cuboid, you get this term. You take the surface area of this top face, you get this term. So the change in the surface area of the entire cuboid is related to the second invariant of C. Okay. And finally, what is this? Lambda 1, lambda 2, lambda 3 is the volume, and we know that this is also equal to determinant of this C. Okay. So these are the three invariants. It will not matter. Now I've also expressed them in terms of coordinate systems, but it will not matter which coordinate system you choose. C11, C12, and C13, and all those things, they will come out to be different in different coordinate systems. So it doesn't matter which coordinate system you choose. If you calculate these three invariants, they are not going to change. Okay. So that's the physical significance of the components of C. What does F do? It takes some vectors, stretches them in some direction, and rotates them. What does C do? C takes some infinitesimal vectors and just measures the stretches along the diagonal stretches of the area changes in the volume. Okay. So using all this information, you can find out, you can define a measure of strain. And by the way, here for those of you who did not take 570, I've mentioned how to calculate determinant in terms of the components, where this epsilon is called a permutation tensor. This is a third order tensor, or a third order matrix, we should say, which is equal to 1 if the I, j, and k are arranged in a cyclic manner, which is equal to 0 if any of I is equal to j or I is equal to k. If any two are equal, then it's 0. If the order is exactly acyclic, then it is equal to -1. So using this relationship, you can also calculate the determinant of some matrix like this. So now, using all this information, we are going to define a measure of strain. So this strain is called the Lagrangian strain tensor. There's another similar strain that is called Eulerian strain tensor, but we are going to just stick to this one. So this is again the same definition that we had before. This is coming from this definition. This is the definition that said that this quantity must be equal to 0 if there is to be no straining. So if we take this quantity and define it to be equal to E, and there's a half a factor, then this quantity is a measure of strain. This will try to measure the pure stretches only. It will not be affected by rigid body rotations or anything. Okay, and if you expand, or if you just substitute C is equal to F transpose F into this equation, and remember that F is actually equal to I plus grad U, then you can also simplify it further to something that you might recognize. Is equal it, Lagrangian strain is equal to half times grad U transpose, and there is this quadratic term which is the nonlinear term in the definition of this strain tensor. But keep in mind that this is exact. Okay, this is geometrically exact. We are not making any small deformation assumptions. So it doesn't matter how your body deforms. If you use this definition, you will obtain a measure of strain. Okay, and this is the definition that we have been using, or you might have been using throughout your undergraduate studies. All that we are doing here is neglecting the nonlinear term. Okay, so if you neglect the nonlinear term, what you're left with is this. But there are a lot of consequences of neglecting this nonlinear term. So normally we don't even think about all these kinematics, and we just assume this definition, find out stresses, strains. We don't distinguish between deformed configuration versus undeformed configuration, and that can sometimes lead to trouble when you're trying to solve and things are not converging. Why are they not converging? Those kinds of things. So that's why I went through the details of all these kinematics. So what we'll do is take one example, and we'll do this as a in-class exercise. So here, just take out I guess a piece of paper, and just write your name on that piece of paper, and in 5 minutes I'll talk more about this. But all I'm asking you to do is, here is this two-dimensional body. You can try to imagine there's a third dimension into the screen, and this body is going to deform in a rigid way. So there's going to be a rigid body translation. So this origin will translate from here to here, and then we are also going to rotate it by some small amount theta. We're going to just apply a rigid body rotation. And that map, if you go to any point in the original configuration, big X, you can find out its final location using this expression. So all that this expression is saying is that this big X is equal to x1, x2, x3, and the small x is going to be given by this first term, and small x2 is given by this second term, and small x3 is just equal to big X3. Okay, so this pretty much defines how the body is going to move. If you give me a point in the original location, I can find out where it went. So what I want you to do is to try to find out what this deformation gradient is going to be. And as soon as you're done, you can just turn in that sheet of paper and make sure you write your name on it. I just count this as one in-class assignment. That will be a bonus to your final score, whatever you get. And if you have any questions, just go ahead and ask. It's not an exam or anything. done? Yep, you can just turn it, start it up. Can you take that, please? Let's take another minute and then we can talk about it. So this is coming straight from the definition of F. You can, those of you who are done, you can turn it in. Yeah, U and V are just constant scalars. They don't depend upon X. All right, let's hand it in and then we can talk about it. That's okay if you didn't get it, it doesn't matter. Can you please pass it up? All right, so what I was asking you to do here was to just use the definition of F that we talked about. So so the definition of F that we had here in kinematics right here. So I was telling you that F is, to calculate F, all that you need to do is take the partial derivatives of x, of small x, with respect to big X. And in terms of matrices, that can be expressed as like this. So small x with respect to big X, all these diagonal terms are the same variable, and the off diagonal terms, you have to take the corresponding derivative. So if you do that, you get derivative of this small x1 with respect to big X1, that's cosine theta, that goes right here. Derivative of this with respect to x2, that's minus sine theta. There is no x3, so we have a 0. Similarly, you move to the second term, derivative of this with respect to big X1, that is plus sine theta, that's right here. Derivative of this with respect to x2, that's cosine theta, and no x3. And finally, here, the only term you will get is 1. So this is the expression for F that you could calculate if you have the map. Now we know that this map is representing a pure rigid body rotation, okay? So if we try to calculate the stresses, calculate the strains, then we should not get any strain. The strain that we get should be equal to 0. So using this definition of F, we can also take a F transpose F. This was the green deformation tensor. and that, if you calculate, turns out to be identity. And according to the measure of strain that we had, the green Lagrangian strain, which is C minus I, right? Right here, C minus I, that will go to 0, and we don't even need the half. So epsilon, or this big E, which is the Lagrangian strain, is equal to 0, which shows that even if you have a rigid body rotation, you will get the geometrically exact strain will give you 0. On the other hand, if you were to take a linearized assumption, so let's say our theta, this theta is very small, and we are going to approximate this map or this deformation gradient with only linear terms. So if we approximate this gradient only with the linear terms, what we get is cosine theta goes to 1, and the sine theta, that goes to theta. Okay, so this becomes the definition or the approximation of f when it is linearized. And when you take C is equal to F transpose F, you get theta square terms on the diagonal. It is not equal to identity, and therefore the correct measure of strain turns out not to be 0, but the linearized strain tensor would still be 0. So in effect, what we are doing here is we are making an approximation, but we just ensure that our linearized strain tensor still remains 0. So the correct strain measure would not be 0, but the linearized strain measure is 0. But this would not hold in case of general deformations. If you are trying to find out the geometrically exact strains using the true deformation map, then you would have to calculate, you would have to take into account all the nonlinear terms, and then you would get the correct definition of strain. Okay. So that's mostly about kinematics. Now I've gone through, the entire kinematics in almost one lecture. So obviously there is a lot more to this, and all that I'm trying to do here is to give you some sort of a background to keep in mind about what is all there to kinematics. But if you have never seen all this material before, then try to go back, make sure you understand at least what we've talked about in the lecture, and then if you need to know more, then you'll have to dig in a little bit. All right, so there's another condition that is somewhat related to kinematics, and that's called compatibility of strains. Now, how many of you have heard of compatibility conditions? Okay, this is something that actually most of you would have heard most likely in your undergraduate in mechanics of materials or solid mechanics whenever you took that. But the idea here is that what we are trying to do is we are trying to find conditions when does a measure of strain correspond to a displacement, correspond to a real displacement. So now normally the way that we have talked about kinematics, we said that we will start with a deformation map. If you give me the deformation map phi, if you tell me where big X goes to small x, then I can find out a measure of strain. But how about, and this is automatically satisfied, we don't need to satisfy any compatibility if we start out with phi. But on the other hand, there are other types of formulations where people say that my strain is also unknown, so I'm going to solve for my strains. Once I solve for my strains, I'm going to try to figure out what is the displacement or what is the deformation that this strain corresponds to. Now you know that this strain has 9 components, right? And the displacement or the deformation has only 3 components. This is a tensor, this is a vector. So 9 versus 3. So how do we make sure that these 9 components actually correspond to a real displacement? And that's the That's the condition of compatibility that we are going to try to find out. So another way to interpret that is in this way. So if you go to any point in the deformed configuration, which is the blue rhombus, and this is or parallelogram, you have this original uh, black configuration. The components of this linearized strain tensor, they can be interpreted with these diagonal components are just stretches along x, y, z. And these off-diagonal terms are actually equal to their approximate measures of the change in angle. Okay, so these are this epsilon xy is half of this, and this is the engineering strain measure that you might be used to. So that's the physical way of looking at it. The condition that we are trying to find is, now that we have this strain, if we were to stack all of these parallelograms next to each other, right? If we know that this point or there's a point in space, and there's a square and it deforms to a small parallelogram. If we stack all of these points together, does the body stay continuous, or does it now start to have some cracks? And because this deformation has to be quote unquote compatible with the next point, and that has to be compatible with the next point, and so on. So that's the condition of compatibility that we're talking about here. And one of the conditions can be derived simply like this. So epsilon xx, which is defined as partial of u with respect to x, and again I'm not taking it with respect to big X because here we are talking only about the compatibility conditions in small strain. The compatibility conditions in exact strain are actually very complicated. So we are going to restrict this in terms of small strain, and then the distinction between big X and small x does not come in. So epsilon xx can be represented like this. If you take the double derivative of this with respect to y, what you get is del cube u del x, that was the definition of u, and you take another derivative with y twice. Similarly, you have EYY. If you take the double derivative with respect to x, you get this. Now just add these two terms. So we are going to add this, and on the right hand side, what you will see is that you can take dx dy out common, and what you will be left with is epsilon xy. So this is one condition that tells you the relationship that must hold between exx, eyy, and exy. So this is one condition of compatibility. That involves only x and y. So similarly, you can get two more equations in terms of y and z, x and z. Okay, so that gives us three conditions of compatibility immediately. And another relationship that another set of relationships that we get is by considering this. So you have exy, which is defined like this. Now you take the derivative of exy with respect to z. So that can be represented with these terms, and I'm going to call this relationship as a one relationship. And you take derivative of eyz with respect to x, that's this, and exz with respect to y, which is this. So now I'm going to take the sum of this term, subtract this term, and add this term. So what you get is this relationship. This is the relationship that must hold between the components of exx, exy, eyz, and exz. So this is another set of conditions. So similarly, if you take or if you switch the combinations, let's say this is minus, this is plus, and this is plus, then you will get another equation. And finally, you take the third combination, you will get a third equation. So what this is it gives you three equations here, three types of equations here, and three types of equations here, for a total of 6 conditions of compatibility. And that when you consider that this strain tensor has 9 components minus 6 conditions of compatibility, it leaves out 3 degrees of freedom, and those 3 degrees of freedom will be your deformation map. So if your strain satisfies all these conditions, then there will be a map or a displacement, a real displacement that this strain will correspond to. If it violates these conditions, then your real, then there might be cracks or overlaps in your deformation. Okay, but if you go the forward route, if you calculate the map and then try to calculate the strains, you don't have to worry about compatibility. It is automatically satisfied. Okay. So all right, let's stop here, and next time I'll finish out some material models, and we'll start with actually one-dimensional finite elements. Okay? All right, see you on Friday.